Right, so in the last graph theory video, if you recall, we ended the video with a corollary, and the theorem to which it was a corollary, that theorem gives us some equivalent conditions for a graph to be a tree. So let's see another such corollary to that same theorem. Here T is a tree and G is any graph satisfying this inequality. That is, the minimum degree of G is at least 1 less than the order of T. Then T is a subgraph of G. That is, G has a subgraph isomorphic to T. This technically correct statement that G has a subgraph isomorphic to T can also more loosely be expressed like this subgraph relation. That's because we do not distinguish between isomorphic graphs. So let us now see the proof. The proof is by induction on the order of T. We apply induction on the order of T. Now before we proceed, note one thing, that although it has not been mentioned explicitly in the statement, but G is non-empty. The fact that we are mentioning the minimum degree of G means G is non-empty, because in the empty graph there is no vertex, and as such the empty graph has no minimum or maximum degree. Okay, so what is the minimum possible value of the order of T? Because a tree is by definition a non-empty graph. Okay, and non-emptiness itself is coming from the fact that by definition a tree is a connected graph, and connected graphs are defined to be non-empty graphs. Okay, with some extra conditions. So that's why the minimum value of this order is 1. When order of T is equal to 1, T has only one vertex. Okay, so this is our T, just one vertex. There you can, if you want, you can consider other trees having only a single vertex, but up to isomorphism you can clearly see there is only one tree having a single vertex. Okay, now since G is non-empty, we can choose any vertex V in G. Okay, because G is a non-empty graph, so we can choose any vertex V in G. This vertex V is a subgraph of G isomorphic to T. Naturally, because that single vertex V can be regarded as a subgraph of G. It is a subgraph of G, and that is isomorphic to that single vertex T. Note one thing, that although up to isomorphism in this case there is only one tree, but the graph G can be actually any non-empty graph. If you are wondering what happened to this restriction, in this case the restriction does not restrict at all. Let us see why. since our T has only one vertex, so we are allowed to consider those graphs G that satisfy this. Now, in any non-empty graph, the minimum degree is of course always greater than or equal to 0. That's because any degree by definition is a non-negative integer. So here all non-empty graphs can be taken in place of this G. So although we have a single choice for T, but your G can be, for example, this may be taken as your G, or this also may be taken as your G, say some other G prime. Now these are non-isomorphic graphs. This one is a tree, this one is not. Any one of them can be taken in place of G. So what we are saying that since G is non-empty, so we can choose one vertex, say this vertex V in G, or for example this vertex V in G. As subgraphs, these single vertices in G and G prime, each one of them is isomorphic to this. So that means our claim is true when T has only one vertex, and that is the basis of our induction. Okay, now we are going to make the induction hypothesis. Assume that the claim is true for any tree T with order of T equal to n and any graph G with the minimum degree of G greater than or equal to the order of T minus 1. Don't forget that the statement is also about G. It's about both T and G related in this way, where n is some positive integer. This is our induction hypothesis in full detail. Now let's use another letter, say S, be a tree such that the order of S is n plus 1. Okay, and let G be a graph with the minimum degree of G greater than or equal to the order of S minus 1, which is n. Okay, now we have to prove that there is a subgraph in this G that is isomorphic to S. And here at this stage we will take the help of one corollary we have seen in the previous video. By corollary 152, the vertices of S can be enumerated as V1, V2, etc. Vn plus 1 such that Vi has a unique neighbor. You can recall what that corollary is. It allows us to enumerate the vertices so that if you choose any vertex, enumerate the vertices of a tree, okay? So that when you choose any vertex except the first one, it has a unique neighbor among the previous vertices. That Vi has, okay, I think I have already run out of ink. Vi has a unique neighbor in the induced subgraph, this. For each I lying between 2 and n plus 1. Okay. In particular, Vn plus 1 has a unique neighbor. Say, let's call that Vk in this induced subgraph, subtree. However, the fact that this is a subtree will, we cannot immediately say that it's a subtree, it's a tree, but now it will become apparent why it's a tree. Okay. Let us now see what the situation is. This is our S, which is some tree, and here we have the vertices, say V1, V2, etc. There are many vertices. Say here we have Vk, Vn, and we have Vn plus 1. Okay. Ideally I should have drawn Vn plus 1 inside S. Now Vn plus 1 has a unique neighbor Vk. So this induced subgraph is this, and Vn plus 1 has a unique neighbor in Vk. Now we are claiming that this fact implies that Vn plus 1 is a leaf, is a pendant vertex, that is a vertex having degree 1. Why? Because if that's not the case, then Vn plus 1 will be adjacent to something else, and since that something else must come from here, so there will be some Vi to which Vn plus 1 is adjacent, besides being adjacent to Vk. Okay, but then this uniqueness is violated. Then Vn plus 1 does not have a unique neighbor Vk in this induced subgraph. So that's why there is no other choice, and Vn plus 1 must be a leaf. Thus, Vn plus 1 must be a leaf. Okay. Now, what is the benefit of having a leaf? The benefit is that if you remove Vn plus 1 from S, the resulting graph will stay connected. It will not be disconnected, and that is because a leaf is not a cut vertex. So Vn plus 1 is not a cut vertex, and hence S minus Vn plus 1 is a tree. This thing, since it's not a cut vertex, so first of all its removal keeps S minus Vn plus 1 a connected graph. Now because that is a connected graph and is a subgraph of a tree S, so that should also be acyclic. It cannot have a cycle, because otherwise S itself will have a cycle. So that's why S minus Vn plus 1 is a connected acyclic graph, so it's a tree. Now note that S minus Vn plus 1 has n vertices. So can we now apply the induction hypothesis? We can, but before doing so we should make sure that, don't forget that we already had one G. So let's draw that G here, and this G satisfies that condition that its minimum degree is greater than or equal to I can't remember, have we already written this condition? Minimum degree of G is greater than or equal to this, and hence this is equal to n. I think we have written this thing back then when we were starting the induction step. If not, please write this. Okay. So this is our G. Now you can see one thing, that this n is greater than n minus 1, and n minus 1 is nothing but this. Because there are n vertices in S minus Vn plus 1. This is S minus Vn plus 1. So not only does the tree S minus Vn plus 1 has n vertices, but the original graph G also satisfies that inequality that we need in order to be, in order to apply the induction hypothesis. So now we can apply the induction hypothesis and say that our graph G has a subgraph S prime isomorphic to S minus Vn plus 1. So we will have to write these things. Since the minimum degree of G is greater than or equal to this, we perhaps we have already written it before. This is greater than or equal to n, which is greater than n minus 1, and that is equal to this minus 1. The induction hypothesis implies that G has a subgraph S prime isomorphic to S minus Vn plus 1. Okay. Let Vk prime be the vertex in S prime corresponding to Vk. We are saying that S minus Vn plus 1, this thing, is isomorphic to S prime. So that means corresponding to Vk, here also there will be a vertex Vk prime. There must be some isomorphism, right? In that isomorphism, Vk prime corresponds to Vk. That is, that isomorphism maps Vk onto Vk prime, or it maps the Vk prime onto Vk. Right. Now, note that we have almost got a copy of our original S here. We are only short of one vertex. Now, if we get a vertex here in G that is not in S prime and that is adjacent to this, then we are done, because then taking this vertex also into account along with this S prime, we will get a copy of S. Now the question is, does such a vertex exist? Since degree of Vk prime, I must okay, degree of Vk prime, yes, degree of Vk prime in G is clearly greater than or equal to the minimum degree of G, and which according to our calculations here is greater than or equal to n. That means in the graph G, the degree of Vk prime should be at least n. Now, how many vertices are there in S prime? Because S prime is isomorphic to S minus Vn plus 1, so the number of vertices in S prime and the number of vertices in this tree are the same. That means there are n vertices in S minus Vn plus 1, so n vertices in S prime. Okay. Among those n vertices, Vk prime is one vertex. That itself is one vertex. So what is the maximum degree Vk prime can have in S prime? What do you think? Since Vk prime cannot be adjacent to itself, there are no loops. So at most it can be adjacent to all the other vertices in S prime. How many other vertices are there? N minus 1, because the number of vertices in S prime is n. So in S prime, Vk prime can have degree at most n minus 1. Okay. However, the degree of Vk prime in G, not in S prime, in G is at least n. So that extra degree, or maybe there may be more extra degrees, because the actual degree of Vk prime in S prime may not be equal to n minus 1, it may be much less than that. So whatever be the case, we will get extra degrees of Vk prime. So those extra degrees cannot possibly come from within S prime. It has to come from outside of S prime. That is, there should be at least one vertex in G that is not in S prime and that is adjacent to Vk prime. And that's what we were seeking. Right. So since this and the degree of Vk prime in S prime is this is less than or equal to this, which is equal to n minus 1, there must be at least one vertex, say let us call that vertex W, in G minus S prime that is adjacent to Vk prime in G. Adjacent in G to Vk prime. But then S prime plus W, the subgraph of G obtained by adding the vertex W along with, of course, whatever but there is one more problem, no? We cannot just simply say that we are adding W, because that would be okay. So instead of writing like this, we can write inwards, but then S prime, the vertex W and the edge Vk prime W form a subgraph of G that is isomorphic to S. So this completes the induction. so it completes the proof. Why did we not write s prime plus w? It's because s prime is a tree that we know. However, if you include w, there is no guarantee that the resulting graph will also be a tree. Maybe in G, because G itself is not given to be a tree, so in G maybe, just maybe, W is adjacent to some other vertex in S prime. So if you bring everything else that W has along with W, you may not end up with a tree. So that's why, to avoid that, we are saying that S prime, the vertex W, and this edge, these three things form a subgraph of G that is a tree and that is isomorphic to our S. Okay, and that gives us the proof. Next, we see the concept of a rooted tree. We won't see much, we will only see a few things, and then I would unfortunately have to stop the video because I'm not getting enough time to go through these things. I'm having some other work. At some point I will get time, so then we will come back to these things. The way we should do these things, I mean, the way one should go through these things, it amounts to having some minimum amount of content, right, that I'm not having right now. I don't have that time. Anyway, sometimes let's see what the next thing is. It is convenient to consider one vertex of a tree as a special vertex. Such a vertex is then called a root or the root. The root of the tree. A tree with a fixed root R is called a rooted tree. Okay, maybe you are interested in something that demands one vertex to be in the tree to be treated as something special. We call such a vertex the root. Once we identify one such vertex, we take one such vertex conveniently as a special vertex, then that vertex is called a root, and the tree along with that vertex considered as a special vertex is called a rooted tree. Writing x less than or equal to y for this thing, for x belonging to R T Y, then defines a partial ordering on the vertex set of the tree, the tree order. Oh, and let's write with the fixed vertex R a tree T. The tree order associated with T and R. Okay, all these things will become clear. Let's just first write things down and then we will try to understand. We shall think of this ordering as expressing height. In this way, if x is less than y, if x is less than y, we say that x lies below y in T. Okay, let's just draw one figure and try to understand this much at least. Say we have a tree that looks like this. Okay, so this is one tree and say this is our distinguished vertex. This is our tree T and this is the root R. So along with this root, T is a rooted tree. Now what we are saying here, writing x less than or equal to y if x belongs to R T y, what does it mean? This is our R, of course. Say this vertex is y. Now we know that between any two vertices in a tree there is a unique path, right, which is a part of the tree. So between R and Y there is this unique path. and that unique path is written as RTY. If X is a vertex in that unique path, say if X, this is X, then we say that X is less than or equal to Y. Note that X can be R also and X can be Y also. Okay, in all such cases we say that X is less than or equal to Y. In fact, that's how we define X less than or equal to Y. So this relation, so this way of relating to vertices gives us a partial order relation on the vertex set of T, on V of T, using which we can say, for example, this vertex is less than or equal to that vertex, and you can, I think, understand visually how this relation works and why we are saying something called height here. Starting from the root, if you draw the tree in such a way that the root is the bottom vertex, which is at the lowest level, then the heights start from that root. Okay, I have not yet said anything about height, but you can understand that the further we go from the root, the higher the vertex is in this relation. Okay, so for example, Y is greater than or equal to X because Y is further away from R than X is, and that is the partial order relation. Why we say it's a partial order? Because any two vertices may not be comparable. If you arbitrarily choose any two vertices, say you choose this vertex and this vertex, let's call them U1 and U2, then you cannot say U1 is less than or equal to U2 or U2 is less than or equal to U1. They are not comparable in this ordered relation. For that to happen, say if you want this to happen, then according to the definition of this relation, U1 must belong to RTU2. Let's see what RTU2 is. RTU2 is this path, and U1 does not belong to this path. So U1 is not less than or equal to RTU2. U1 is not less than or equal to U2. Just like that, U2 is also not less than or equal to U1. So there is an order relation, but it is a partial order. It's not a total order. Okay, all the things are not at once linearly captured by the order. All the vertices don't come at once like that. It is not like the order relation less than or equal to we have, for example, in on the set of natural numbers. On the set of natural numbers, although we have, I forgot whether we are considering or not considering 0. I think we are considering 0 as a part of the set of natural numbers. So although this set has infinitely many elements, but here the order is a total order relation. You can think this also as a graph, a tree, although there are infinitely many points, so in our definition it will not be covered, but just simply for the sake of analogy, we can think of it like this, where you can think of this as root, and then naturally you can understand 1 is less than or equal to 2. In fact, it's strictly less than 2, but let's just forget about those fine details for now. 1 is less than or equal to 2, 2 is less than or equal to 3, 1 is less than or equal to 3. So any two elements are comparable. Here that is not the case. So that's why it's the partial order, that is not a total order. And by the way, a partial order is a relation that is reflexive. That is, if you are considering reflexive partial orders, that is reflexive, antisymmetry and transitive. And that extra condition that any two elements are comparable, that totality is not present here for this particular tree and this order. Okay, now let us move ahead. The tree order, okay, so this order is called the tree order, tree dash order, tree order associated with the tree T and that distinguished root R. Not one thing, that you can change R. You can in fact take any vertex as your root, then the entire thing will change. So this tree order depends not only on the tree but also on the chosen root. We shall think of this ordering as expressing height. If x is less than y, we say that x lies below y, which is very clear here. If we draw like this, then x is actually below y. What else can we say about this order? We will study partial orders, Zorn's lemma and its equivalence with some of the other statements like axiom of choice at one point in Terence Tau's analysis. Okay, those parts have not come yet. We will learn about those things. Okay, so height also we call this, which is defined to be the set of those elements x in the tree that are less than or equal to y, the down closure of y. And this the up closure of x. So that means what? If you say if your y is this, the down closure of y is the set of those vertices that are less than or equal to y. So clearly in this particular instance, the down closure of y will be what? Y of course will be there, x and r. Okay, and up closure of x. Up closure of x for this case will be x is of course there, x is less than or equal to x, x is less than or equal to y, and x is also less than or equal to u1 as well as u2. Note that do you see something else? The up closure of R is the entire tree. And note one more thing, there is a distinction between the down closure of a vertex and the up closure of a vertex. Of course they are two different things, but still if you just look at the graph, the down closure of a vertex is always a path, but the up closure of a vertex is not necessarily a path. In this case, you see, this is not a path, but it may be a path. For example, the up closure of y is a path, okay, but the down closure is always a path. In the terminology of order theory, this means that the down closure of a vertex is a linearly ordered set or a chain, a set of elements in a partial order where any two elements are comparable. If you take any two of these three elements, three vertices x, y and r, you can say that one of them is less than or equal to the other. Now in a partial order, not any two elements are comparable. For example, u1 and u2 are not comparable. So if you consider this subset, say u1, u2, y, x, r, that is not a linearly ordered set, that is not a line, okay, that is a tree like this, it has branches. So linearly ordered sets are called chains. So that's what down closures are. Down closures are always chain, up closures are not necessarily chains. Note that the root is the least element. The root is less than or equal to every vertex, is the least element in this partial order. Okay. The leaves of T are the maximal elements. The leaves are the maximal elements, these. You already know that there is a distinction between maximum and maximal. Maximum means absolute, okay, it is greater than or equal to everything else. Here, however, we use in a partially ordered set, we use the adjective maximal. Maximal means an element such that there is no greater element. So you can see that although if you think in terms of height, this leaf, for example, it has height only 1. So it's not that big in this order, in this tree order. However, you can see, although I cannot say that this is bigger than this because these two are not comparable, but in terms of height, this element has much more height than this one. It has height 1, 2, 3. But despite this difference, both of them are maximal elements, because if you consider any of one of them, there is no element that is strictly greater than any one of them. So in that sense they are maximal. There is no other greater. In its own universe of each of these leaves belongs to a linearly ordered universe, sub-universe. For example, this one. If we start with the root, it belongs to this universe. In this universe, it's the largest. In this universe, this is the largest. In this universe, this is the largest. So in that sense, they are maximal elements. The ends of any edge of T are comparable. Yes. Let's see why this is true also. Let's take any edge. Let us take this edge. Its ends are x and y. We have already seen x is less than or equal to y. But why is this happening? Why is x and y? Why are x and y comparable but u1 and u2 are not? You see, if you think of y and if you think of r, there is a unique path joining r and y, and in that path we have x, which is a neighbor of y, and that's why they are ends of an edge. So that's why x and y are comparable. So that means in a general rooted tree, if you take any edge like this and the root is there somewhere, so there will be a unique path joining this point, this vertex and the root r. Now it may be the case that that path goes like this, avoiding this vertex, or this vertex is a part of that path. Exactly one of these two things will happen. In any case, you can see that these two will be comparable. In this case, this will be greater than or equal to this, and in this case, this will be less than or equal to this. So that's why the ends of any two edge are comparable. And the down closure of every vertex is a chain. We have already mentioned this. Chain, and we already know chain is set of pairwise comparable vertices or pairwise comparable elements in general in a partially ordered set. The author writes proofs of these facts, which does not of course mean that you have to write rigorous proofs. Understanding them like this and seeing in your mind that in the general case also something similar happens is enough. And lastly, the vertices at a distance k, at distance k from r, have height k. Are said to have height k, and they form the kth level of the rooted tree T. Okay, so let me just show it here itself. The 0th level has only this vertex, the root itself, always. The first level has these two vertices. Okay. The second level consists of those vertices that are at distance 2 from R. That means 1 to this one, 1 to this one, 1 to this one. Okay, that is the second level. And you can clearly see that the remaining vertices form the third level. So the vertices at the second level, each one of them has height 2 from R. So I would have to just end the video here itself. After this, there is one notion of a rooted tree being normal inside a graph, because you can find trees inside graphs which are subgraphs of a given graph. We have already seen such things, spanning trees, for example. So there is a notion of a rooted tree being normal in a graph, and that idea can be very nicely used to know many things about a graph. There are strong relationships between the separation properties of a rooted tree and the graph in which it is a subgraph. Okay, so we will see those things in the next graph theory video. So today is Thursday. Friday. On Saturday we again have our Gregory Tilly's algebra exercises. So that will be all for tonight. If you want to say something about these things or about anything else, you can write in the comment section below. So see you on Saturday. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.